All right, everyone. So we'll continue today. Last time we covered diodes, just simply how diodes kind of work, how we can kind of use them. So let's go ahead and let's start kind of getting into something where things start changing. Up till now, we've been working with direct current. But there's another way, which is alternating current. So let's go ahead and let's kind of just define how, what direct current looks like. It's what we've been using up to this point. So if we go ahead and look at DC, or direct current, we'll give ourselves a constant voltage source. And we'll just do the most simple circuit we possibly can, which is a constant voltage source connected to a resistor. And let's go ahead and label this as V sub S. It's got a positive and a minus. Okay, and when you look at the current going through this, current always goes from a higher voltage to a lower voltage, so we expect it to go down. And so we expect the current to only go in this one direction through this resistor. And so the result of this on a graph, if you plot the voltage being applied to this resistor with respect to time, then our applied voltage V sub S will simply be a flat line at whatever value this is, right? So if this was 10 volts, we would have a flat line 10 volts with respect to time for as long as this goes on, right? Now alternating current, on the other hand, let's go ahead and introduce a new voltage symbol over here. We're going to use an AC voltage source. That'll be comprised of a circle with a little sine wave squiggly mark on the inside. And we'll construct the same exact circuit. Just apply that to a resistor. Okay, now here's what's going to happen. If we go ahead and plot what the voltage is doing, this voltage source, and I'll go ahead and call it VAC for now. Let's look at what this ends up looking like on a graph with respect to time. The AC voltage will actually be going up and down, and we'll always take it centered to 0 over here, 0 volts. Now we do have to go ahead and kind of define what this peak value is there, and I'll get to that in a moment. But for right now, let's go ahead and kind of look at a couple of things here with AC. So we can sort of break this down into two different things that are happening, or two different sections. We're going to call this the positive alternation. And we'll go ahead and list the other half of this waveform as the negative alternation. So what's going on here is that half of the time the voltage being applied to this resistor is positive. That's during the positive alternation. And the other half of the time, the voltage being applied to this resistor is in the negative. During the negative alternation is all negative. So what we have is two different situations. So I can go ahead and break this down into two separate circuits here, just for the sake of breaking these up, where our AC voltage source is positive during that positive alternation. In other words, we can consider the polarity such that during this positive alternation over here, when our voltage applied is all positive, we can consider our voltage source to be positive up here, minus down here. And as such, applied to this resistor, the voltage is positive up here, minus down here, and the current is going in this direction. Whereas during the negative alternation, our applied voltage is always negative. And so now we can flip our polarity, positive on the bottom, minus on the top. And now you can see the current is actually going up. So this current arrow here is going up. So when we look at our original AC circuit over here, we actually have this situation where half of the time the current is going in one direction and the other half of the time it's going in the other direction. Okay, depending on whether we're in the positive alternation or the negative alternation. So I'll show that as a arrow with two heads over there. Okay. So we have current going in both directions. That's actually where we get this name, alternating current. So even though on the graph I plotted voltage, voltage and current are directly proportional to each other. So we need to go ahead now and kind of quantify what the magnitude of this is. Now, when we're talking about DC, it's incredibly easy, because if this was 10 volts, we'd be at 10 volts all the way across. But over here, notice that if this was 10 volts, well, is 10 volts up here? 10 volts down here? What is the voltage? We want to quantify this with a magnitude. So we need to go ahead and kind of establish a couple of different conventions. Now, there are multiple ways to refer to the magnitude of this AC voltage source, and that's what we're going to go ahead and get to. Now, with an AC voltage source, we actually have three different ways that we can refer to that magnitude. Okay, so we have what's called peak voltage, which I'll be referring to as V peak. We have peak to peak voltage, which I'll refer to as V sub peak to peak. And we have a third one, root mean square, which we would refer to as VRMS. Now, I'll go ahead and talk about these first two, and then we'll get into some detail and explain the last one. But the first two are pretty easy, so let's go ahead and kind of go over that. So again, let's go ahead and set up our really simple circuit over here. And we're going to say VAC is equal to we'll use 10 volts peak. Okay, so now we're going to be actually specifying the magnitude of this AC voltage source as a peak voltage. Now, if we go ahead and look at that on a graph, well, the voltage applied is going to go all the way up to 10 volts and all the way down to minus 10 volts. So when we say 10 volts peak, what we're saying is that the highest voltage this sine wave ever hits is 10 volts. And equally, it goes all the way down to the same magnitude in the negative direction of negative 10 volts. So that's what's meant by 10 volts peak. Now, we also have another way to specify this exact same voltage. We could refer to it as a peak-to-peak voltage. Now, the peak-to-peak voltage is just the difference between the highest point and the lowest point. Whereas the peak voltage was only in one direction. So this same voltage source is also 20 volts peak to peak. Okay, so peak and peak-to-peak voltage is pretty straightforward. You're just going with the highest positive value for our peak voltage, and our peak-to-peak voltage is from the highest to the lowest, including our negative. Okay, so peak-to-peak is kind of like your absolute magnitude difference between the highest point and the lowest point, and your peak voltage is just the highest positive voltage. Okay, so that takes care of peak voltage and peak-to-peak voltage. However, there is another way to specify the magnitude which ends up being a lot more useful in many cases, and that's the root mean square. Now, for the root mean square, I'm going to go ahead and use the example of our wall outlet. Now, if you didn't know this already, what comes out of your wall is not direct current, it's alternating current. Alternating current just makes it much easier to transmit over long distances at a very high voltage to get power over to your house. So what comes out of your wall if you think about your standard wall outlet over here, you have essentially these two prongs at the top. The third one is actually safety. So we actually have some names for these that come out of your wall outlet. So if you think about your three prongs, you actually have a hot, you have a neutral, and you have what I'm going to call safety. Now, they refer to this as ground, but I want to keep a good differentiation between this and the ground of previous circuits, because it's a completely different beast altogether. So don't even worry about this third prong when it comes to your outlet. All we care about is the hot and the neutral. Between the hot and the neutral is where you're getting your AC voltage from. Now, I'm going to go ahead and ask a question. Obviously, no one can answer it in this video because it's a video. So, what is the magnitude that comes out of your wall outlet? 110, 120, 150, 200 volts, 100 volts. If you're in Europe, 220 or 240. So what is that? What is that number? Okay, so think about that for a second. Think of a number. I'm thinking of a number as well. We're going to go with 120 volts. Notice I haven't said peak, peak to peak, or RMS. So what on earth is this, right? So let's go ahead, let's draw a graph. Okay, now our voltage that comes out obviously is an AC voltage. Looks like a sine wave because it is. And I've drawn 1.5 cycles over here. Notice at this point, the cycle actually repeats itself. And it would continue on indefinitely. So I'm going to go ahead and just give you what this answer is. Turns out the peak voltage is 170 volts. That's what comes out of your outlet. 170 volts. Peak. Okay, what's that in peak to peak voltage? Well, obviously it goes up to 170 volts, so it also goes down to minus 170 volts. So our peak to peak voltage is 340. Oh, I'm going to have to squish this in. Okay, imagine this is all on the same line. Peak to peak voltage, 340 volts peak to peak, which is the same as 170 volts peak, which apparently is also the same as this 120 volts RMS. And remember, RMS stands for root mean square. And so commonly when you see anything that's rated to plug into your wall, it says 120 volts RMS. They don't say 170 volts peak. And there's a reason for this. It's because RMS tends to be more useful for AC voltages, especially when it comes into things that plug into your wall. But we need to go ahead and define this. Now, if we look at where 120 volts RMS is on this graph, remember these all three are the same exact quantity. It's right about here. 120 volts. Now, here's the problem. If I go ahead and apply an AC voltage to this resistor, and I want to talk about the power dissipated by this. PR. We know it's equal to I times V. However, when we substitute in 170 volts for V to calculate the power, we end up getting the wrong answer. Okay, I'll say that again. If we were to calculate, and let's just say 170 volts peak with a 10 ohm resistor, if we go ahead and calculate what the voltage is by plugging in 170 volts, well, first we'd have to calculate what the current is. We would say I is equal to, let's see, 170 volts divided by 10 ohms equals 17 amps. By the way, this is already incorrect, but we'll run with it. PR is equal to 17 amps times 170 volts. Whatever number that comes up with is just wrong. We actually can't do that. The reason we can't is, notice, that's only the power dissipated at this one point. That's a momentary fraction of time compared to the rest of the time that this voltage is changing, right? Sometimes we have 0 volts applied. In fact, we have 0 volts applied as much as we have 170 and minus 170 applied. So this calculation just doesn't work. So our goal for RMS is to create an average voltage. Okay, it's a fancy way of describing the magnitude of this voltage as an average voltage. Something that we can use to get Ohm's law and our power equation back. Here's the problem. I should say another problem. It's a problem on top of another problem. If I average this, what is my average value? Think about that for a second. Half of the time I'm going up, I'm positive, and then I hit this 170 volts peak. The other half of the time I go all the way to minus 170 volts peak. What's my average voltage here? It's 0. Okay, that's our problem. The average of a sine wave is always 0, assuming that we go up to 100, up to the maximum as much as we go down to the minimum. As long as these two values are the same, the average is always 0, which kind of sucks. Okay, so we can't just average the voltage and expect to get a correct value. Because if I go ahead and I put 0 in here for our voltage, we would get 0 for our current. And that's just not true. Same thing, once we plug that back in here, we get 0 power being dissipated. Okay? Now, I know for a fact if I plug a resistor in, a light bulb, a load, anything into my wall outlet, I'm going to get some power dissipated from it. So obviously, this just can't be true. The average is not 0. Well, that's where we go ahead and cleverly start to use this idea of root mean square. So remember, the goal here, we're trying to find an average voltage. And we can do this. Let's start off with our AC voltage source. And we're just going to, oh, I made that way too large. Scratch that. Sorry about that. In fact, I'm close enough to a fresh sheet of paper. I'm just going to redraw that. And I'll do 1.5 cycles again. Okay, so this is V peak. Now, remember, if we average this, we're gonna get 0. So what can we do in order to get rid of that problem where when we average this, we get 0? Well, what if we square it? Well, if we go ahead and square it, now our AC voltage is now all positive. And the peak value is now V peak squared. Okay? So we just squared it so that we don't, when we average this, we don't get 0. All right, next up. How do we take the average of something? We'll just half it. So now we're going to go ahead and average, or mean. Well, if we go ahead and average this, cutting it right down the middle, now we get half our V peak squared. Okay. However, keep in mind this average that we just did isn't representative of our original value. It's only representative of our squared value. So we're going to have to undo the square. Well, how do you undo a square? You take the root of it. Root it to undo the squaring procedure that we did earlier. Once you've done that, now you're going to get a smaller value that's actually representative of the average of your original AC. So this is why we call it root mean square. Because we did the square, the mean, and the root. Why is it backwards? I think it might have to do with language in other countries. Root, mean, square. Okay, so this is what we say, or what we mean when we're talking about RMS. Now, we need to go ahead and write out an equation for this. Real straightforward one. VRMS is equal to 1 over root 2 times the peak voltage. And this, I would suggest to just remember. Now, similarly, there's an approximation that I use. VRMS equals 0.707 times V peak. I know some older electrical engineers that can do this in their head when it comes to any voltage that they're talking about. It's really quite impressive. However, 99% of the time when I'm doing this, I have a calculator in hand, and it's very quick for me to just go 0.707 times whatever my max voltage gives me my RMS. Okay, so the whole point of this is that now we can actually get back Ohm's law and our power equation. So now let's go ahead and say 120 volts RMS, which is equal to 170 volts peak, which is equal to 340 volts peak to peak. Those are all three ways that we can represent this AC voltage that's coming out of our outlet. Now, if I go ahead and apply this to a light bulb, and for all practical purposes, a light bulb is no different than a resistor. Light bulbs get hot, and if they get hot enough, it'll give off light, which is exactly what's happening in a light bulb. So now we have our two equations that are back. VRMS is equal to IRMS times R. And the average power is equal to IRMS times VRMS. Okay, so now we have our Ohm's law and power equations back, and they work. Okay, so that's how we can go ahead and come up with an average value for referring to an AC voltage. Okay, so let's go ahead and continue. I don't want to just leave it off there with describing RMS AC voltage and not doing anything fun with it. This is actually why I introduced diodes last time, so that we can actually do something with this. Now, let's go ahead and set up a very simple circuit. This circuit's got a name. It's called a DiodeClipper circuit. We're going to give ourselves an AC voltage, a diode, and a resistor. And we're going to be looking at Vin and we're going to be looking at Vout Now, when you measure a voltage, you always have to measure it with respect to something. In this case, I'm going to be measuring Vin and Vout. I'm going to plot those on a graph, and I'm going to be referring to both of those voltages with respect to this point down here. Now, this point down here, is the same voltage all across here. So I can actually look at V out as being the voltage between these two terminals. And if you notice, the voltage between these two terminals, V out, is the same as the voltage across this resistor. So we're going to go ahead and look at V in with respect to V out. Now the easiest way, and let me actually put in a voltage over here. I need some AC voltage. Let's make this 10 volts peak. I'm just going to leave it in peak voltage because I think that's a little easier to work with right now than RMS, at least for a first time pass of looking at this. And we're going to go ahead and say that this is an ideal diode, meaning it has a V sub F equal to 0 volts from our last lecture, and we're just going to use the first approximation. We can look at the second approximation, but as a first pass to see and learn what's going on here and the technique for kind of analyzing this kind of a circuit, the first approximation is all I'm going to go ahead and cover for now. In 311, we'll actually be picking up, and we'll get a lot more into this. Now, the easy way to analyze this circuit is to actually look at this circuit and how it behaves in two different cases. Remember, we have a positive alternation and we have a negative alternation. So if we study this circuit from those two cases, we'll be able to fully understand what's going on. So what I'm going to do down here is let's go ahead and set ourselves up a graph where we can plot V in versus V out. Now, keep in mind, V in is the voltage at this point, which is the same as our VAC, which is 10 volts peak. So if we're going to plot V in, V in goes all the way up to 10 volts, all the way down to minus 10, all the way back up to positive 10, and we'll just do 1.5 cycles here. So this is 10 volts, and this is V in. This is time. And notice I haven't paid any attention to how long it takes for this, because in this case it doesn't matter. We'll be looking at time a little later and how this AC gets quantified with respect to time. But for right now, let's go ahead and let's just look at this. Okay, so in fact, let me go back over here and let's say we have two different cases that we can study. The first one is the positive alternation, and down here is the negative alternation. Okay. So if we go ahead and just break this up into two cases where we're looking at the positive alternation, the negative alternation, makes a lot of sense for this circuit. Reason for that is because this AC voltage source during the positive alternation is behaving as though it has positive up here, minus down here, causing the current to go in one direction, and the other half of the time during the negative alternation, it's positive down here, minus up here, and the current's actually going backwards. Okay. So let's go ahead and let's draw the circuit twice, see what happens. Okay, there's my circuit. I'm looking at V out versus V in. And now let's go ahead and ask ourselves, during the positive alternation, what happens in this circuit? Well, we know we have positive up here, minus over here, and this is causing the current to go in this direction. And now my question is, what is this diode doing? Now remember, we're working with the first approximation, so we're just going to treat this diode like a switch. Is the current going in the direction such that this diode will conduct? Is it behaving like a closed switch or an open switch? Well, notice it's going in the correct direction. This diode is being forward biased. Hence, it's conducting. So I is going to be greater than 0. Now we need to go ahead and ask ourselves, what does V out do in this situation? Well, what happens if V in is 1 volt? What is V out? Well, assuming that this is a perfect diode with 0 volts of a forward voltage, right? That's what's meant by an ideal diode. This is the first approximation. Then what is the voltage drop across this diode? 0 volts. Which means now you can think of this, we're just applying 1 volt directly to this resistor. So when we have 1 volt for V in, V out is also 1 volt. If V in is 2 volts, V out is 2 volts. If V in is 3 volts, V out is 3 volts. You see where I'm going with this, right? As our V in is applied, as our AC voltage is applied, this is going up, and we go all the way up to 10 volts. Well, if we go all the way up to 10 volts, we get 10 volts on V out. So in other words, if we're going to go ahead and plot V out over here, it follows that curve exactly. When it's 1 volt, we get 1 volt. When it's 10 volts, we get 10 volts. Okay. That's what happens during the positive alternation. Now during the negative alternation, our polarity of our AC voltage is going to flip. So now let's go ahead, let's analyze this circuit again, but now we're going to do it for the negative alternation. So I'll go ahead, redraw this. And now during the negative alternation, our polarity has flipped from our AC voltage source. That means the current is now trying to go in this direction. Now what's this diode going to do when the current is trying to go back through it? Well, remember, to a first approximation, this diode is not going to be conducting. This diode is reverse biased. If it's reverse biased, there's no way I can get any current going through this, so I is just equal to 0. So now let's go ahead and let's look at what happens to V out. Remember, V out again is just the voltage drop across R. So if I have 0 ohms going through R, what's my voltage drop across it? Well, V equals IR, and if I is always 0, then V is always 0. So V out is always 0. So if I get 1 volt applied, I get 0 volts from V out. If I apply 2 volts, and actually, I should probably change that. Well, no, because the polarity is taking care of that, so don't worry about it. As this, I was looking at the graph, and the graph, because the graph goes negative, but this negative is already taken care of by me putting the positive sign down here and the minus up there. So I can legally say this is 1 volt, this is 2 volts, and it's fine. So when we get 1 volt applied, we get 0 volts out. When we get 2 volts applied, we get 0 volts out. When we get 3 volts applied, same thing, 0 volts out. And if we have all the way up to our negative 10 volts down here, we get 0 volts out. Looks like we are losing half of our waveform. Once we get back to the positive alternation, same as before, the voltage goes all the way up and comes all the way back down. And let me go ahead and list this as V out. Okay, so that's how we go ahead and analyze a circuit like this. We break it up into its 2 cases, study what happens in each one of those cases, and aggregate our results to develop our full understanding of how this circuit works. Now, let's kind of talk a little bit about higher level. What's the purpose of all this? Why are we all here? Well, we're all here to get good jobs, right? And why are we here to get good jobs? So that we can make good money. Why are we here to make good money? So we can live comfortably and have a house and a significant other and maybe raise a family. So that's the purpose of all this, right? So we can raise a family. That's my deep thoughts for the day. Okay. Remember I named this circuit, right? It's the DiodeClipper circuit. Why? And I didn't give it this name. It's always had this name for as long as diodes have been around. So why is it a clipper circuit? Well, it's a clipper circuit because it's clipping this whole part of the waveform. This is being clipped. It's being clipped just by virtue of the orientation of this diode. The circuit remains the same, but our AC switches between the positive alternation, the negative alternation, 50-50. Does that half the time. Now, what is it that we are losing here? Well, we're clipping all negative voltages. Our V out always stays at this 0 whenever the applied voltage goes negative. Well, that actually is useful, but let's go ahead, let's name this circuit a little further. DiodeClipper negative clipping. Negative clipping because we're losing the negative portion of this waveform. Now, you might be wondering, still, why is this useful? Believe me, it is. If you think about this circuit, we have this AC being applied to the input, and the output of this circuit is always positive. So in other words, no negative voltages can get past this circuit. Now, if you think about your laptop, and if you think about your cell phone, for fun I should draw a flip phone here. What's one of those? Laptop, phone. Let's see. If you're taking 211, you probably have taken 201. If you've taken 201, you've used an FPGA board. Made some digital circuits on this guy. And let's see, what else? Let's just say computer in general. I'll just say PC. What else am I thinking of? LCDs, printers. The list kind of goes on. What do all of these have in common? They all use direct current. Your laptop battery charges off a direct current. So does your phone battery. Your FPGA board and all digital devices work off of DC, direct current. Your personal computer, your PC, your desktop, your Mac, whatever it is that you use, is also direct current. Your LCDs, your printers, your keyboards, your mice, your car, everything works off of DC. You can't really do digital circuits in AC. You can't make digital devices, phones, PCs, laptops. You can't do all that with AC. You have to have DC. Now DC, of course, looks like a flat line, where AC is alternating. Now AC we need for power distribution. These are power poles. And I'll attempt to draw a house. Now to get power from the power factory to your house, you need AC. And the reason for this is because these long lines, a wire is not a perfect 0 ohms. I've been treating it as such on the board, and for small circuits, the resistance is negligible. However, the resistance of these enormous mile-long lines starts to add up. Now, if you think about DC and you think about current flowing through a wire, think of it like a bunch of marbles. And I push it in this direction, and the marble pops out, right? My electrons, I'm pushing them all in the same direction. However, the resistance of those lines starts to make less of a difference if I wiggle these electrons back and forth. So I just give them a little push in that direction. Then I give them a little push in the other direction. So essentially I'm wiggling these back and forth. I'm not trying to just keep on pushing them all the way through. And so the effects of resistance on your power transmission lines starts to become less of an issue, much less of an issue with AC than it does for DC. But DC is horribly useful for my laptops, phones, PCs, and all my digital devices and appliances and everything that makes the world great today. So I have to be able to take this AC and turn it into DC. I need a process to do this. Now, granted, this is a far cry from a nice long straight line, but it is the very beginnings of doing so. At the very least, I've gotten rid of all of my negative voltage, and I've made it at least 0. So what I'm saying is, this is AC, and this is kind of like DC. And we do have a formal name for this, pulsating DC. It's direct current. The electrons are all being pushed in one direction. Positive, no push, positive, no push. And the electrons are all going in one direction. So at least we've done one thing right here when we're talking about converting AC to DC. So this very simple circuit is the beginnings of every single modern power supply that we use in every single type of digital device. Like, there's not much these days that actually plugs into your outlets that purely runs off of AC. Motors do. Tesla invented the first AC motor, and it was what made everything possible, because the beginnings of power production is more than just light bulbs. Lights are nice, but being able to do mechanical work with your electricity is even better. So as far as turn of the century, 1910s, 1920s, and coming into the modern day, being able to have an AC motor, a motor that works off of power, that's easy to transmit over long distances, is not just nice, it's necessary for everything that's happened in the past 100 years. But as we get more modern day and we have all of these digital devices, they really want DC, and so we need a way to convert the two. And this is the very start with that DiodeClipper circuit. Okay, so I'm going to go ahead and leave that there. I think I've covered more than enough for the day. Hopefully you kind of enjoy this a little more. It's not just so mechanical, but we're actually starting to get into more useful circuits that are going to grow with us, and we're going to get into that a lot more in 311. And hopefully we're going to paint this nice picture. All right. So everyone, please take care of yourselves. Stay safe. Keep washing those hands. Take care of your families and those around you. And I'll see you guys next time. Take care.